Welcome to our tutorial on kinetic molecular theory. We're going to relate this a lot to gases, and the kinetic molecular theory is the theory that all substances have molecules that are constantly moving. And we've talked a little bit about this previously, but there are three assumptions of the kinetic theory as it applies to gases. The word kinetic itself refers to motion. If the energy of an object has motion, then we call that having kinetic energy. According to the kinetic theory, all matter consists of tiny particles that are in constant motion. And the particles of a gas are usually molecules or atoms. So the assumptions that we have when the kinetic theory is being applied to gases are the following. The particles in a gas are considered to be small, hard spheres with insignificant volume. And that doesn't sound like a lot, but if you think about it, if you have a sphere without volume, that's really kind of an oxymoron. But because the particles of a gas are so small, we consider them to have no volume when we're talking about the kinetic molecular theory. The next part is that all collisions between these particles of a gas are perfectly elastic. And what it means to be elastic is that within the gas, the particles are going to be relatively far apart. And when they hit one another, there are going to be no attractive forces or repulsive forces. And instead, the collisions that they have are going to give the energy to each other perfectly. They're going to share that energy perfectly. And so the overall effect is that these collisions, there's no energy lost, there's no energy made. The average energy of the gas stays constant. The next is that the motion of the particles in the gas is extremely rapid, constant, and random. And this is why gases can escape from their containers that when their container is open. It's what gives us pressure that allows the balloon to stay inflated. So these particles being in motion create this pressure within the container. So what are the factors affecting gases? There are four factors affecting the gases. The first one is the number of moles, and really we can think of this as the amount of gas. And so n from now on, this small n, is going to represent the number of moles of a substance. The next variable involved in gases is its volume. We can change the volume of a container and the gas is still going to fill it because of that rapid constant motion. The next is temperature, and we measure temperature of gases in what we call kelvins. And just so that we are clear, we have to remember that the degrees Celsius of a substance plus 273 equals the amount of kelvins. Now, we don't use degrees kelvins, it's just kelvins. So something that is at freezing temperature, if we have water at freezing temperature Celsius, 0 degrees, when we add 273, water freezes at 273 Kelvin. Boiling point of water is 100 degrees Celsius, and so if we add 273 to that, water would boil at 373 Kelvin. Finally, we have pressure. And pressure is due to that rapid constant motion and the particles hitting the walls of the container. That creates pressure. And our SI unit for that is pascals. Now there are several others, and we're about to talk about those as well. There are several other units that we can use for pressure. And a lot of times we will also use atmospheres or millimeters of mercury. And millimeters of mercury equals something called torr. And then because this is our SI unit, another one that we use is called kilopascals. So those are all units of pressure. So as I said, the SI unit of pressure is the Pascal. And normal atmospheric pressure is about 100,000 Pascal. And because that number is so large, that's why a lot of times we'll use kilopascals instead. Remember that kilo is 1,000 times as great as the base unit. Again, two older units of measure are millimeters of mercury, and I also said that millimeters of mercury is equal to torr. So if I have 1 millimeter of mercury, that's going to be equal to 1 torr. It's just a measurement of pressure. And then the final one is atmospheres. One atmosphere, one standard atmosphere, is the same as 760 millimeters of mercury. So we talk about standard temperature and pressure. This is what standard pressure is. Standard pressure is 1 atmosphere, and that's equal to 760 millimeters of mercury, or 101.3 kilopascals. That would be the same as 101,300 pascals, or be equal to 760 torr. We can use these things to go in between one another, and so we could say that 1 atmosphere equals 760 millimeters of mercury to do a conversion between pressures. Standard temperature and pressure are defined as the temperature of 0 degrees Celsius and a pressure of 100.3 kilopascals, or 1 atmosphere. So that's STP. So let's look at trying to convert some units of pressure. A pressure gauge records pressure of 450 kilopascals. Let's convert this measurement to atmospheres, or millimeters of mercury. So when we do that, we get our list of knowns. We know that the pressure is 450 kilopascals. We know that 1 atmosphere equals 101.3 kilopascals, and we also know that 1 atmosphere equals 760 millimeters of mercury. We got kilopascals. We want to know the pressure in atmospheres and the pressure in millimeters of mercury. So we go ahead and use our conversion factors. To convert from kilopascals to, find my cursor here, kilopascals to atmospheres, we're going to use this conversion factor that goes back to what we talked about with standard pressure. If we want to go to kilopascals to millimeters of mercury, I'm going to use this conversion factor, or this truth. So when we do that, we start with our given, and we really can take this over 1 times 1 atmosphere over 101.3 kilopascals to cancel out our units, and we come up with 4.4 atmospheres. For part B, when we're taking from kilopascals and going to millimeters of mercury, again, we put our given over 1, and we use our truth to cancel out our units, and we come up with 3,400 millimeters of mercury, or 3.4 times 10 to the third millimeters of mercury. That's the end of our video today. In class, we will be applying a lot of this to gases and gas laws. Thanks.